Hello everyone. In this video we are going to discuss indeed an example of designing a PI controller. Here we have the system given in the form of a transfer function GP of s, which is equal to 1 over s plus 1 times s plus 2 times s plus 10. So basically our transfer function, the open loop transfer function that we have, has three poles at -1, -2, and -10. And we are supposed to design a controller for this system using the Root-Locus approach such that the steady state error for the closed loop system becomes equal to 0 when we have constant reference, let's say the step input in it, and we need to have a damping ratio for the dominant complex pose being equal to 0.174. We will do it through the RL tool, but as the first step we need to draw the Root-Locus plot for this system. We will focus on the positive locus. If I do it, I just do it not precisely here, but the Root-Locus for this system will look like this one. We know that the type of the system is 0, so we have a type 0 system, and therefore the requirement on the steady state error will not be satisfied using a proportional controller. But the requirement on the damping ratio could be satisfied using a proportional controller. We'll do it again through the RL tool, but if we draw the lines which corresponds to this value of damping ratio, then we can pick a value for the K for the proportional controller such that two of the closed loop poles happen to be at these points. And then the third one might be somewhere over here. If you want, we can find out the location for the third one as well. And then since we cannot satisfy the steady state requirement on the error, we would need to increase the type of the system. Okay, so first we'll start by designing a proportional controller to satisfy the transient requirements. And then in order to satisfy the steady state error, we will add an integrator, a pole at the origin, and then a 0 near to the origin. In this way, the type of the system will increase. And then since the 0 is close to the pole, the Root-Locus plot of the system will not change a lot. And then we would need to retune the value for the gain of the controller in order to meet the transient requirements as well, or in order to place the closed loop poles at the same location. Okay, so I already have introduced the system GP of s, and then I also have introduced the design requirement. The damping ratio that I have introduced is equal to, damping ratio is equal to 0.174 as required. And then for the controller, if we set the value to 164.6, you can see that the closed loop poles of the system will be at the intersection of the white and yellow area. In order to satisfy the transient requirements, the dominant closed loop poles should be in the white area, but on the other hand, we try to increase the value of the gain as much as possible in order to improve the steady state error. Well, indeed, in this case, we need to have the closed loop poles right at the intersection of the white and yellow area, yeah? Because the requirement is in terms of having the damping ratio equal to that value, not smaller or bigger than that. All right, so with that value of Kp, we have the closed loop poles here and there, and the third one will be over here. let me switch back to the slides. So by setting kp equal to that value, you can find it out analytically as well if you want, but just to be kind of quick, I use the MATLAB in order to obtain the value. By setting the value kp equal to this value, the desired damping ratio is obtained. And then if you find out the steady state error for the same system, it will be equal to 0.108. So indeed kp, the error constant, will be equal to limit of L of s as s goes towards 0, and this will be equal to limit of 164.6 times 1 over the denominator of the GP as s goes towards 0, and this will be equal to 164.6 over 20, which is 8.23, and steady state error will be equal to 1 over 1 plus kp, which is equal to 1 over 1 plus 8.23, and therefore the steady state error will be equal to 0.108. So now we are happy with the transient requirement, but we need to deal with the steady state error. Therefore, we will add a pole at the origin, which we call as an integrator. And then since we are going to have the PI controller, we will add a 0, and that 0 will be at minus 0.1. Okay. So for now, we just pick the value for the 0. You could probably place the 0 at minus 0.05 as well, or minus 0.15, or minus 0.01. Okay, so it's kind of arbitrary for this example especially. Later we will see that as the 0 moves towards the pole, or as 0 moves far from the pole at the origin, the behavior of the system will be different. Okay, so for now, let's say that we have added a pole at the origin and the 0 at minus 0.1, and then if we readjust the gain of the controller, we will get the value 158.1, and with that value the closed loop pose of the system will be located at the exact same place that we had. So let's introduce the controller. I'm going to add a pole. Let me see if I can right click here. For some reason try again. Okay, now I will add a pole. I would like to get your attention to the changes that happens to the root locus of the system. You see, as soon as I introduce the pole, the root locus of the whole system changed. So we are going to place it at 0. And you see how the root locus has changed. We also need to introduce a 0. So real 0. By default, it's located at -1, and I'm going to change it to 0.1, minus 0.1. And now, if you pay attention, over here you can see that the root locus now looks kind of similar to the original case. And over here we need to To set it to 100, let me just get the exact value that I already have determined. 158.1. 158.1 will give us the sorry for this kind of mess that happened. I'm switching too much between the screens, but I think it will be over now. 158 point one, and let us see what happens to the location of the closed poles of the system. Now we can see that they are at the intersection, okay? And therefore the steady state requirement will be satisfied, and the step response of the system will also give us steady state error equal to 0. For that, I already have drawn the step response of the original system, as you can see over here, indeed with a proportional controller only. So in blue, what you see here is the step response of the closed loop system with the proportional controller with the gain, which gives us the requirement on the damping ratio. For that system, the steady state error will not be 0. And you can see that over here. Yeah? You see that the final value is 0.892, so the steady state error is equal to 0.108. For the second system, we know that the steady state will be equal to 0, even though it is, let me remove, okay. You see that the final value is equal to 1, therefore the steady state error is equal to 0. And you can also see that up to time equal to around 2 seconds, the step response of the two systems are kind of similar to each other, but after that they get different from each other, because for the system with the PI controller, which is shown in red, the steady state error will be equal to 0 at some point. The issue with the PI controller that we have here is that it has a large settling time. Let me remove the steady state characteristics. Okay, now you can see it. It's indeed bigger than 15 seconds. And for the system without the PI controller, the settling time is equal to 5.14 seconds. In other terms, by the introduction of the PI controller, the step response of the system has become quite slow. So it takes a long time for the system to reach its final value. And that's not a nice property. Indeed, we don't want to have our system acting so slowly. Okay, we want it to be quick. Okay, so we know that by the introduction of the PI controller, the response of the system has become slow. And this is due to the fact that we have a very slow pole of T of S, which originates from the integrator. And it's almost cancelled by the 0 of the PI controller. Yeah? Because for the closed loop system now, if I draw the location for the pole and 0 of the system, for the closed loop system, we will have two poles, let's say around here and there, one pole over here, and then there will be a pole pretty close to the origin and pretty close to a 0, which is at minus 0.1. So there will be 1, 0 and 4 number of poles. And if you compare it with the dominant second order system with 2 complex poles over here, the response that we get from the system will be quite slow, and the reason is over here. That's the reason that we have for the low, let's say, low speed or quite slow response of the step response of the system. So what can we do? In order to get rid of this effect, we can, instead of using the PI controller, we can switch to another type of the controller, which is called as lag compensator. Compared to the PI controller, in the case of lag compensator, we don't place the pole of the controller right at the origin, but we place it close to the origin. And then the zero of the controller will be also located close to the pole of the controller, because we don't want again to change the Root-Locus shape of the system. So the basic idea in designing the PI controllers okay, so my system takes some time to respond to my actions. The basic idea in designing the PI and lag controllers is that we keep the Root-Locus of the system as similar as to the original one. We try not to change it. And to achieve this, we need to place the pole and zero of the controller close to each other, because then the phase contribution from those two will kind of cancel each other's effect. Okay, so again, in the case of lag compensator, we will not place the pole at the origin. We will place it at some point like minus PC, and we will have a zero nearby at S plus ZC. In this case, we will improve the steady state behavior of the system by a given factor, and it will depend on the ratio of ZC over PC. So with this, the steady state error will improve, but we are not increasing the type of the system. Okay, so keep this in mind. With the lag, we are not increasing the type of the system, so the amount of the improvement that you get in terms of the steady state error will not be the same as using a PI, because with PI the error will become zero, as we had for the previous example in the case of type 0 system, but with lag it will not become zero. It might become quite small but not zero. But on the other hand, since the pole of the controller in the case of lag is not located at the origin, its effect in terms of increasing the settling time of the system will be better than what we have with the PI. In the next lecture, we will go through how to design a lag compensator in order to improve the steady state behavior of the system without destroying, let's say, the settling time for the step response. Alright, so that's all for this video. In the next video, I will maybe go through this slide again, and then we will see how to design the lag compensator in more details. Thank you for watching, and see you in the next video.